Good afternoon. Okay, let's just wait for the others, okay? Can you hear me? Oh, okay. Can you hear me?
Yes.
Okay. Just, just a moment, okay? Only 17 are present right now. Please change your name. Please type your name in English. The one wearing the blue sleeveless shirt. What's your name? You, the one wearing the blue jersey, basketball shirt. I don't know what do you call it. 19. Let's wait some more. What's his name? Okay. How are you?
I'm fine, thank you.
All right. Good to know. I think. Okay, I think that's it. Only 19 will join today. All right, let's start. Can you see the PowerPoint?
Yes.
All right. So last meeting we had electricity, right? And we had, last week we had components, types of circuit, types of battery arrangement, right? So who can give me the 4 components of a circuit? Who can still remember without looking at your books? Without looking at your books. Who can give me the 4 components?
Battery.
Battery, what else?
Electrical wire.
Electrical wires, what else?
The bulb. Light bulb.
The bulb or light bulb, what else?
Switch.
Switch, very good. Switch, okay? Very good. Nice. Okay, so we have battery, bulb, wire, and switch. Don't forget also their symbols, okay? So for battery, we have the long and the short line. The long line, meaning the positive side of the battery, and the short sign, which is the negative side of the battery. And then we have the light bulb, the wire, which is just a straight line, and then the open switch. But if you draw this line downwards, then it's a closed switch. All right. So we have also learned about the 4 types of circuit. Who can give me? Okay, I'll just give it right
Open
away.
circuit.
Open circuit. What else?
Closed circuit.
What else? Series
Series.
and parallel.
Parallel.
Okay, now I want a volunteer. Who wants to try? I have a question. Emiki, please unmute.
What is it?
Okay, can you please differentiate open and closed circuit? What's the difference? What's the difference between open and
Open
closed?
circuit, the light bulb
I'm sorry?
doesn't work because the electricity cannot pass through.
Okay, very good. So for open circuit like this, the switch is open and so electricity cannot pass or flow through it, okay? But if we say closed circuit, then the light will work. Why? Because electricity can pass through or flow through the switch. Okay, very good. How about the difference between series circuit and parallel circuit? How are they different? Okay, you do this, okay? For series circuit, the light bulbs are side by side, okay? And there is only one path or there is only a single path for the electricity to flow through, whereas in the parallel circuit, we have multiple paths, okay? Do you understand? Okay, so open circuit, electricity cannot flow through it, okay? Electricity is broken, whereas closed circuit, the light bulb will work because electricity can flow through it. Series circuit, single path. Parallel circuit, two or many path or multiple path, okay? I hope that's clear. Now let's proceed to battery arrangement. So we have series and parallel, okay? For series, the period of time that the light bulbs will light up will not change. So in the series, let's just read first. So for series, the period of time that the light bulbs light up will not change. More batteries, the brightness of the light bulb increases. No matter how many batteries, they will be consumed as one. So here, in the series arrangement of batteries, the positive side of the battery will be connected to the negative side of the battery, of another battery, okay? For example, the flashlight, okay? So when we use batteries in the series or serial arrangement, the light bulb will be brighter, okay? But it will not last long. If one battery lasts for 2 hours, let's say 2 hours, even if we add more batteries, they will be consumed as one. So they will only last for 2 hours, even if you put 10 batteries, okay? If they are arranged in a series or serial arrangement. Whereas in parallel, the period of time that the light bulbs light up will be longer. More batteries, the brightness of the light bulb doesn't change. The more you add batteries, the longer it will remain lit. All right. So in parallel series, the light bulb's brightness will not change. However, the time it will light up will change. It will be longer. For example, a battery can last up to 2 hours. And then we arranged 5 batteries in a parallel arrangement. So we have 2 hours, 2 hours, 2 hours, 2 hours, 2 hours. So we can consume the 5 batteries in 10 hours. Do you get it? Okay. So that's just the difference. In series, brighter bulb. Parallel series, no change. Okay? In the series, the time will not change even if you put many batteries. Even if you put 100 batteries, the time it will be consumed will still be the same. Whereas in the parallel, the more you add batteries, the longer it will light up. All right. I hope it's clear to you. Clear? No. Okay. Um, well, then let's start a new topic, which is all about still about electricity, but a new subtopic. So we have electrical conductors and insulators. Okay. Electrical conductors and insulators. How are they different? Okay. So conductors, who wants to read? Ananshai, do you want to read? Okay, none. Okay, so for conductors, they allow electric current to flow easily. This will be um, this will be discussed further later on. Okay, for insulators, they do not allow electricity to pass through them. So take a look at their colors. For conductors, it's green, meaning go. Okay, electricity can pass through them. It's go. And for insulator, it's red, meaning stop. They cannot pass through them. Okay. So for you to better understand, let's watch this video.
Do you think this dill pickle is a conductor?
Hi. Listen properly, okay? Watch closely. Ready? Okay. I hope you are.
Do you think this dill pickle is a conductor or an insulator? How about this cup of water? Welcome to Moo Moo Math and Science. And is it a conductor or insulator? A conductor is an object or material that allows the flow of negatively charged electrons in one or more directions, which results in electric current. An electrical insulator is a material in which the electrons do not flow freely. What we will do in this video is take a look at some different objects. We have some metals, some plastics, a Sharpie. How about a pickle and some water? We will hook it up to some electricity and see if it is a conductor or an insulator. Up first, we have copper. Hook it up, and yes, it's a conductor. How about this piece of plastic? Flip the switch, nothing happens. It is going to be an insulator. Now we move on to another piece of metal. It's aluminum. Flip the switch, and yes, it is a conductor. Now, how about some wood? Hook it up, flip the switch, nothing happens. So it is an insulator. After the block of wood, let's try this. How about we try a Sharpie? It's plastic, it's hooked up, we go to the switch, and nothing happens. So it is an insulator. How about this? Let's try some water. I've got two nails hooked in, I flip the switch, nothing happens. Well, let's modify the water slightly. Let's add some salt. As I add the salt, I pour it in, I go back to the switch. What do you think? Is it going to change? I hit the switch, and yes, it is now a conductor. The salt allows the electrons to move freely. Next, let's try this screwdriver. The reason why I use this, I have plastic on one end, metal on the other. I flip the switch, nothing happens. But now, if I move it to where it is touching metal only, it's now a conductor. So the plastic helps insulate it. How about this? How about the pickle? It has a lot of salt in it. Well, I don't know about that. I plug it in. It smokes a lot. It glows. But I would consider it an insulator. About celery, it kind of tastes salty. Maybe it has enough salt in there. I plug it in and, well, you can see for yourself. Nothing really happens. Well, it does start smoking a little bit. So let's see what happens with celery with 110 volts going through it. Smoking, but it is an insulator. Kind of cool looking, huh? Next, how about the apple? Kind of a dud. Well, not really. It's an insulator. So if you need to insulate, an apple is your option. So I hope that helps. If you'd like to know more about conductors and insulators, this playlist will help. And as always, thanks for watching. And Moo Math uploads a new math and science video.
Okay. So the experiment is called conductor or insulator. What are the things that were mentioned in the video? Can you still remember? The materials that he used in the experiment. Can you remember? No. Wood. What else? Copper. Aluminum. Sharpie or marker. Do you have your books? Please open your book. On page 55. Okay, so we have here an experiment, and since we cannot actually do it, I've shown you a video, right? So the materials here are copper coin, plastic ruler, wooden ruler, paper clip, eraser, graphite, aluminum foil, and handkerchief. All right. So I'm going to show you pictures of the objects mentioned, okay? Look at the screen first. We have copper coin. Of course, it's made out of copper, which is a metal. Next, we have plastic ruler. It's made of plastic. Next, wooden ruler. It's made out of wood. Next, paper clip. Hi. Remember, this is a metal clip with a vinyl coating, okay? So this is a paper clip with vinyl coating. And a vinyl is like a rubber coating, okay? Next, we have eraser or rubber. Next, graphite. Graphite, usually you can see this in your pencil. Okay, when your pencil is very dark, it's a graphite pencil. There could only be two, graphite or lead. Okay, next we have aluminum foil. Do you know aluminum foil? I think you know this. You can see this in the kitchen. And the last one we have handkerchief. Do you know handkerchief? All right. So this one is not handkerchief. Okay, it's handkerchief. Silent D, handkerchief. All right. So now we are going to identify if a material or an object is a conductor or insulator. Okay. All right. So here, the green box, we are going to put here the conductors. And here in the pink box, we are going to put all the insulators. Okay? So we have copper coin, plastic ruler, wooden ruler, paper clip, eraser, granite, aluminum foil, and handkerchief. All right. Copper coin first. Is it green or red?
Green.
Green. All right, very good. So copper coin is a conductor. Very good. So it's a go. Next, plastic ruler.
Red.
Red, very good. Wooden ruler. Wooden ruler.
Red.
Red, very good. How about paper clip?
Green.
Is it green? Paper clip with vinyl coating. It's not metal clip. Paper clip with vinyl coating. It's like a rubber coating. It's insulator, okay? But if we remove the vinyl coating and the metal is the only thing that we're going to use, it will be conductor, okay? Next, eraser or rubber. Green or red? I'm sorry? Green or red?
Red.
Red. Eraser is an insulator. Very good. How about granite? Oh, graphite. How about graphite? What do you think? Any guess?
I think green.
Green. Yes, very good. How about aluminum foil?
Green.
Green. Very good. That's why we use it for cooking. Handkerchief.
Red.
Red. All right. So here we have the different examples of insulator and conductors. So for conductors, you can see copper coin, graphite, and aluminum foil, and metal paper clip. All right. So all those four are examples of metals, and metals are good conductors. Okay. Whereas plastic, wood, and rubber and cloth are not conductors, good conductors of electricity. So they are called insulators. Okay? Do you understand? Do you get me? Okay. Amiki, you better be sure. Okay? All right. All right. So long wires carry electricity from power stations to many buildings such as our homes and schools. So look at the diagram. So here, power plant generates electricity. So electricity comes from different power plants. It can be a dam, hydropower plant. We call it hydropower plant when they use water, or solar power plant when they use sunlight, or wind farms. What else? Nuclear power plants. Okay, those are the different types. And then transformer steps up voltage for transmission. And then it will go through. Can you see this? You can see this on the road, right? Yes. So transmission lines carry electricity long distance, and then another transformer here, but it will step down voltage, and then the electricity will be distributed in our houses, schools, hospital, everywhere. Okay? All right. So most electrical wires are made of metals. This is because metals are electrical conductors. So basing on the video or the experiment on your books, so metals are good electrical conductors. Note, all metals are electrical conductors. You have to remember this, okay? If it's a metal, it's a conductor, okay? All metals are electrical conductors. However, some can conduct electricity better than others. So I have prepared here examples or the top 5 electrical conductors. Okay, best conductors. We have the first silver. Do you know silver? The one we use for our jewelries. Next, we have copper, the one I've shown you, copper coin. Sorry, next we have gold. Do you know gold? Yes, next we have aluminum, like the aluminum foil, or sometimes our pans are made out of aluminum. And calcium. And then here's a trivia, okay? Remember, silver, copper, gold, aluminum, and calcium, okay? There's a trivia right here. Aluminum is the material, sorry, just material, not materials. Give me a moment. Okay. Aluminum is the material used in transmission wire. Do you know transmission wire? The one you see on the streets. Okay. Why do you think so? If aluminum is not the best conductor, why do you think it is used? We've said it, like aluminum is only the fourth best conductor. Why do you think are they used in transmission lines? Any guess? Why do you think? Any idea? No?
Because it's cheap.
Yes, very good. That's one reason. What else? Okay, very good. None. So aluminum, among the five, it is the cheapest. Okay. Silver, it's expensive. Copper is also expensive. It's the least expensive, but it's the second least expensive, but it's still more expensive than aluminum. Gold, it's the most expensive among the five. Okay, and calcium is not possible. Okay, so here, aluminum wires are good conductors of electricity. So that's a proven fact. Actually, they are the fourth best conductors, and it is cheap metal, easily available, light in weight, so they are not heavy, and also very good ductility. So when we say ductility, you can form them into different forms, and then you can stretch and they will not break. Okay? So they are malleable, meaning to say you can form them into different shapes. And then you can also stretch like a rubber and they will not break. Okay? So that's it. Cheap metal, easily available, light in weight, and very good ductility. Okay. Now let's proceed to insulators. Most nonmetals such as plastic, rubber, and wood are electrical insulators. They do not allow electricity to pass through them. Okay, so here's a trivia again. Trivia, rubber is the most commonly used insulator. Okay, why? Because rubber is flexible and it has the ability to be easily bent around corners and enter electrical boxes safely. Again, rubber is used because of its flexibility and ability to easily bend around corners and enter electrical boxes safely. All right. So if you observed or if you can remember the sample of electrical wire I have shown you, it is covered in rubber. Why do you think so? What's the importance of electrical insulators? Hi. Hi. What do you think is the importance of electrical insulators? Why do we wrap our wires with rubber? For example, here, my earphones. It has wires inside, but it is covered in rubber. Why do you think so? What's the importance of insulators? Hi. So electricity will not pass through our body. Okay? That's the reason. So imagine if the wires that we use don't have any insulators and then you hold it and then you plug it in. What do you think will happen to you?
You will get electric shock.
Yes, you will be electrocuted and it's possible for you to die. Okay? All right. So that's one importance of insulators. All right. Now let's proceed to electromagnets. All right. So for electromagnets, let's have here the magnetic force of temporary magnets such as electromagnets can be switched on and off. All right. So electromagnets are temporary magnets, okay? They are not permanent. They are only magnetic when there is electricity applied, okay? Electromagnets depend on the flow of electricity to exert magnetic force. Iron and steel are often used to make electromagnets. So as what I've said, electromagnets are temporary magnets. They are not permanent. So if you unplug or you turn it off, then there is no more magnetism. Okay? Can you still follow? Yes? All right. I hope so. All right, let's watch this video, okay? Watch closely.
Hi, this is Ben Finio with Science Buddies, and if you want to know what an electromagnet is and how they work, then this video is for you. You might already know about regular magnets. They have opposite poles that attract, similar poles that repel, and they can even attract other metal objects that don't attract each other, like these paper clips. You can also take a compass, which is itself a small magnet, and move it around near another magnet, and the needle will point in the direction of the magnetic field. So how does a coil of wire manage to behave the same way? It turns out that moving electrical charge, or current, creates a magnetic field. Watch what happens when I connect this piece of wire to a battery. It makes the compass needle move just like a magnet did, so we know the wire must be creating a magnetic field. This magnetic field takes a circular shape around the wire like this. However, the magnetic field around a single straight wire is very weak, not enough to pick up even one of these paper clips. You can make the magnetic field much stronger by wrapping the wire into a coil called a solenoid. This causes the fields around each individual turn of wire to add up to make a much stronger, more uniform magnetic field similar to that of a bar magnet like this. However, you'll see that this coil of wire is still too weak to pick up an individual paper clip. To make an electromagnet really strong, you need to add a ferromagnetic core like this iron bolt. Ferromagnetic materials have many smaller individual magnetic domains. Normally, these domains are aligned randomly and cancel each other out. However, in the presence of an external magnetic field, these domains align with each other and the external field, making the overall field much stronger. Watch what happens when I insert this iron bolt into the core of my electromagnet. Now it's finally strong enough to pick up a paper clip. Unlike a regular magnet, an electromagnet can be turned on and off by removing the flow of electrical current. If you reverse the direction of the electric current, you reverse the direction of the magnetic field. To change the strength of an electromagnet, you can change the number of turns in the coil, the length of the coil, the amount of current flowing through the coil, or the core material, all of which would make a great science project. Because they have very low resistance, the wires in electromagnets can get very hot, so you should always disconnect them when not in use.
The paper electromagnet in this video was just for a demonstration. You should not try this at home because the paper could actually catch on fire. To see a variety of science projects that use electromagnets.
Okay. So remember, you cannot do this at home, okay? Don't try to do it. All right. I've only shown you the video, but don't do it at home. It's very dangerous, okay? So here's how it works. Here is a diagram. So battery, okay? And then we have the switch. And this one, iron nail or the ferromagnetic material, okay? It can be other materials as long as it's iron or steel, okay? And then we have here the coil of insulated wire. Remember, insulated wire, okay? So if we turn on the battery, if we turn on the switch, the iron nail will become magnetic because of the electricity or current that flows through it, okay? But if we turn it off, then the magnetism is gone. Do you understand? All right, I hope so. All right, so why do we need electromagnets? All right, so electromagnets have many uses and can be found in our daily lives, such as doorbell. So when you ring the doorbell, we are actually using electromagnets, okay? So look here. All right, so this is the switch. If you push it, and then electricity flows through the electromagnet, okay? And then it will boop. Okay, it will attract this. And then it will hit the bell and it rings, okay? So that's one uses electric doorbell. Next we have loudspeakers. Do you know the loudspeakers you use at home? Okay, so they use also electromagnets. Next, junkyards. So last time you have learned about separation, right? Separation of mixture, right? Separation of mixtures. Now, electromagnets are used to separate ions from ores in junkyards, okay? It makes their lives easier, okay? Next, we have for hospitals. They use electromagnets for MRI, okay? So this one is called an MRI. It uses electromagnets to take picture inside of our body. It's like X-ray, okay? All right. And also we have maglev train. So this one can be found in China. All right. So this is the fastest train. It can go up to 600 kilometers per hour. Can you imagine how fast it is? All right. So here it doesn't have wheels. Okay. It doesn't have wheels. It only uses electromagnetism. All right. If you can see here, it's like hanging, right? This one is the bridge, and then the maglev train is like this. And it does not cause any friction, so it's very fast. Okay? All right. I hope you don't have any more questions. Any questions about electromagnets? None? All right. If so, let's proceed to our last topic, which is all about static electricity. Okay. So for you to better understand, let's have this. When we rub an object against another object, one of the objects lose negative charges while the other object gains negative charges. So the most common experiment here is the balloon. When you rub a balloon into your clothes, it will create static electricity, okay? So as a result, the objects become oppositely charged. These charges remain in an area, and the difference in the electrical charges can cause static electricity. Okay, let's watch this video. It's not an experiment.
On the wall, it is not going to stay. It doesn't matter if I set it here and let go really slowly, or if I push really hard. Every time I let go, the balloon will drop. But if I take this balloon and then rub it around on a fuzzy blanket for a few minutes, watch what happens. The balloon is sticking to the wall now because when we were rubbing the balloon against the blanket, we were gathering extra electrons from the blanket onto the balloon. Rubber is not a conductor of electricity, so that means if you get electrons, these small little particles on the rubber, they don't get passed through, they gather and create static. Once that balloon has that charge, then it's attracted to things that are more neutral, things that don't have a charge, such as its fabric. Now, it's not a permanent thing. That balloon will not stay here forever. Eventually, those electrons will dissipate. They will go out into the wall or into the air. The balloon will lose its charge and then it will fall. How long it takes depends on the temperature, the humidity, and of course, how much charge that balloon gathered in the first place. This is a fun science demonstration, but it's not an experiment because we didn't change anything and we're not measuring anything.
Okay.
If you'd like to make
So, do you want to try this at home? Do you want to try this activity? You can do it with a piece of paper like this. If you just want to know static electricity, okay? You can rip papers into small pieces, okay? And then get a comb. Do you know a comb? The one you use in your hair. Do I have one? Oh, I cannot. Okay, here. Okay, do you know? Comb. And then you rub it. Rub, 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 rub. And then put it near the paper. It will attract the paper. Okay? Just rub. Make sure that the pieces of paper are small, okay? And then you rub. And then it will attract the paper. It should be long enough, okay? All right. So you can do that later on when we finish our class, if you want to do it. It's just an activity. All right. We still have another. All right. So here, a charged object can attract or repel another object. So positive and positive does not attract, they repel each other, okay? Negative and negative, they repel each other, but positive and negative attract each other, or negative plus positive. Okay? That's why we always say opposite attracts. Okay? Positive and positive cannot. Okay? Negative and negative cannot. But positive and negative, they can attract each other. Okay? Do you understand? No. Yes? Okay. So here's a trivia. Lightning is caused by static electricity. Okay, so it's here in your book. Positive charges form at the top of the cloud and negative charges form at the bottom of the cloud. When the charge difference becomes too great, a spark is formed. It is observed as lightning. So if I ask you to give me an example of things that are caused that is caused by static electricity, you say lightning. Okay? All right. So what other objects use static electricity? Okay. Let's have, do you know this? Photocopier. Okay. So when you finish photocopying, actually, just fill the paper. It feels very odd because it has static electricity. When you finish printing, when you finish using this, and then you hold the paper, put it near your hair, it will attract your hair, some of your hair. Okay, and the last one we have, do you know this? Air purifier. Okay, an air purifier has a negatively charged filter to attract positively charged dust particles. So that's how it works. Okay, no questions? No questions? Okay. You don't have any questions? I have. Okay. Non-bonsai. Just tell me if they will repel or attract. Okay? Okay, non. Positive and positive. Repel or attract?
Repel.
Very good. Tira pop. Tira pop. Please unmute. Now, who else? Amiki. Positive and negative. Will they repel or attract each other? Positive and negative. Repel or attract? Any guess? Come on. Will they repel or attract each other? They will attract each other, okay? Don't forget this one. Opposite attracts, okay? If the charge is not the same, then they will attract. Positive plus negative, they will attract each other. Negative plus positive, they will attract each other. But if they are the same, if the charge are the same, the positive and positive, they will repel each other. Negative and negative, they will repel each other. Okay? All right. So if you don't have any more questions, that ends our class for today. Next meeting, we are going to have, just give me a moment, for P6. Okay, so for next meeting, we are going to have chapter review. Okay? We are going to answer your workbook. All right. So that's it for today. Thank you for listening.
Thank you, teacher. See you again.
All right. Bye-bye. See you next time.
Thank you, teacher. See you again next time.
Okay, bye.
Thank you, teacher. See you again next time.
You're welcome. Bye.